In this experiment, we investigate how surface color and finish affect the absorption and emission of infrared radiation using a Leslie cube thermometer or infrared sensor, hot water, and a stopwatch. Hot objects lose energy by infrared radiation, and the rate depends not only on temperature, but also on the nature of the surface, with dark matte surfaces generally emitting and absorbing more than light shiny surfaces. Our aim is to measure how much infrared each face of the cube emits at the same temperature, and to compare this with a simple absorption test using black and shiny metal plates under identical lighting. The independent variable is the surface color and finish of each face, and the dependent variable is the infrared intensity or temperature measured at a fixed distance, while the control variables include the cube material, the volume and initial temperature of water, the distance and angle of the detector, the room conditions, and the time allowed before each reading. The Leslie cube has 4 faces, typically matte black, white, dull metal, and shiny metal, and we keep the cube still while bringing the detector to the same marked distance from the center of each face. We place the cube on a heat-proof mat, fill it quickly with hot water, for example, at about 80 degrees Celsius, start timing immediately, and wait the same time interval before each reading so that every face is tested at the same average internal temperature. We point the infrared sensor or thermometer square onto the first face at a fixed distance, such as 20 centimeters, record the reading. Then repeat exactly for the remaining faces without changing distance or angle, and we randomize the order of faces to reduce cooling bias. We repeat the set 3 times, refilling with hot water to restore the starting temperature, and then calculate mean values so that random fluctuations are reduced. To demonstrate absorption, we place 2 identical metal plates, one painted matte black and one polished shiny, at the same distance from an infrared lamp or strong lamp. Switch the lamp on together and measure the rise in temperature over the same time interval using identical thermometers or a thermal camera. The black plate warms faster and to a higher temperature, showing that dark matte surfaces absorb radiation more effectively, while the shiny plate warms more slowly because it reflects more incident radiation. For emission, the matte black face of the cube gives the largest infrared reading at the same temperature, while the shiny metal face gives the smallest, confirming that good absorbers are also good emitters. Safety considerations include handling hot water with care, keeping electrical equipment and the lamp away from spills, using a heat-proof mat, and allowing the apparatus to cool before moving it. Sources of error include the cube cooling between readings, slight changes in distance or angle, reflections from nearby objects, and non-uniform internal temperature. So we minimize these by marking the detector position, shielding stray reflections, stirring the water gently before sealing the lid, and taking repeated averages. The conclusion is that surface color and finish strongly affect thermal radiation, with dark matte surfaces being the best absorbers and emitters, and light shiny surfaces being the poorest, which is why radiators are often painted dark, and vacuum flasks use shiny surfaces to reduce heat loss by radiation.